are in listen-only mode.
Good day, everyone, and welcome to the DOE Fuel Cell Technologies Office monthly webinar series. Today's installment is titled H2 at Scale, Deeply Decarbonizing Our Energy System. My name is Chris Worth, and I am the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides, will be posted to our website in about 10 days. We will send out an email to attendees once those are posted to the site. Next slide, please. All attendees will be on mute throughout the webinar, so please submit your questions via the question box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. Next slide, please. With that, I would like to introduce our DOE host, Erica Gupta, joining us from the Department of Energy headquarters in Washington, D.C. Erica is a technology manager in the Fuel Cell Technologies office. It's a pleasure to have you, Erica. Good afternoon.
Thank you, Chris, and thank you everyone for joining our webinar. I'm pleased to introduce today's speaker. Brian Pivovar is Fuel Cell Group Manager in the Chemistry and Nanosciences Center at the National Renewable Energy Laboratory. Brian oversees both electrolysis and fuel cell R&D at NREL. He has been a pioneer in several areas of fuel cell development for vehicle applications, taking on leadership roles and organizing workshops for the Department of Energy on sub-freezing effects, alkaline membranes, and extended surface electrocatalysts. For the past year, Brian has led this multi-lab national laboratory team pursuing hydrogen at scale as a pathway for deeply decarbonizing our energy system that explores the importance of hydrogen in transportation and other energy sectors. He previously led fuel cell R&D at Los Alamos National Laboratory and received the 2012 Tobias Young Investigator Award. Brian, thank you for giving us this presentation today. I will now turn it over to you.
Thank you, Erica. It's my pleasure to get this opportunity to talk to everybody on the webinar about hydrogen at scale. This has been an effort that's been 14 national labs all listed below on this slide, and I'll go through the evolution and other parts of the program. But first I'd like to acknowledge the Department of Energy who's helped allow us to put this together, especially the places listed here, the Office of Energy Efficiency and Renewable Energy, ERE, particularly the Fuel Cell Transportation the Fuel Cell Technologies Office and the Transportation Working Group, but also the Office of Nuclear Energy, NE, and the Office of Electricity Delivery and Energy Reliability, OE. We've also had engagement in this process with FE and the Office of Science. So in this webinar, I'm looking to go through a number of specific aspects of hydrogen at scale. The first thing is to describe to you what we mean by hydrogen at scale, and then to talk to you about why it's needed and why it's needed now and today. We'll then go through what we're hoping to accomplish with hydrogen at scale and how we plan to do that, and in particular why government, national labs, academia, and industry all together are needed to make it happen. And then finally, we'll talk about what success looks like and what the impacts of hydrogen at scale can be. So there are several, starting along the lines of getting to hydrogen at scale, there's going to be several factors that actually impact the status of hydrogen. First is that hydrogen is not new. It's seen a lot of ups and downs in terms of prominence and prestige, but almost everybody, and I'm sure everybody on this webinar, has preconceived opinions about hydrogen. And one of the difficulties for hydrogen has always been the complexity of it and also the changing environment that is going on both within the world, within the research community, and then within government. But hydrogen is also different, and that's an issue for people as well. And this is a perception issue. It includes factors such as safety, but it goes beyond safety. And then there's also a concern over the infrastructure and the cost of hydrogen. So when it comes to hydrogen as an energy carrier, the fact that it's different is going to be one of the issues that comes up. The other issues that are shown on this slide are hydrogen's kind of an outsider in that it doesn't necessarily have champions or established revenue. It certainly does in a few areas that will be talked about later in this webinar. But unlike battery technologies or other types of competition with hydrogen, the community isn't as established. And then finally, especially for renewable hydrogen. And finally, the politics of hydrogen are also quite interesting. I've found the polarization of hydrogen to be pretty amazing. And so when we go through this webinar, each one of these things will be discussed at some level of detail. So before I get into that, we'll talk about a few hydrogen fun facts, because it's really the perception of hydrogen and the knowledge of hydrogen that's one of the things that makes it more difficult to take on. One thing that people don't necessarily realize is that today 10 million metric tons of domestic production of hydrogen occur in the US today. So it's a huge number. About half of that goes into upgrading crude oil to make gasoline, and the other half of that goes into combining with nitrogen to make ammonia for fertilizer. That number is actually 2% of US energy, and it's approximately equal to the solar and wind combined today. So while you see wind turbines when you're driving through rural areas, when you see solar panels on houses or in solar fields, you don't necessarily think of the large amount of hydrogen that's being used, because it's being an energy upgrade to the gasoline that you're driving your vehicle on, or it's going into the foods that we're eating through the fertilization of the lands with ammonia. The other thing is that while handling hydrogen comes with different types of challenges, we handle it in large amounts today, and there's actually over 1,600 miles of pipeline for hydrogen in the US. A lot of this is located either in California, where the refineries are, or in the Louisiana, Houston types of corridors, where most of it's either used for ammonia or crude oil upgrading. And finally, it's being used in over 1,000 fuel cell vehicles with several million of miles of vehicle travel. I'm guessing that maybe many of you have already driven such vehicles. And today, we actually have fueling stations for vehicles open to the public. And so these are things that the general public doesn't necessarily always connect with, but this is where hydrogen sits today, and it's much more advanced than a lot of people think it is. So that brings us kind of to a transition to talk about hydrogen at scale as a national lab-led big idea. For those of you who are unfamiliar, big ideas are identified by national lab teams as high impact areas that are basically either underemphasized or lacking a champion within a DOE portfolio in some sort of a way, perhaps because of the way the DOE is set up, or perhaps because of changing dynamics in terms of R&D needs and what the future holds. This big idea process culminated in a DOE National Lab Big Idea Summit, which was earlier this year in April. Hydrogen at Scale was presented, and the slides that are coming forward, a lot of them showed up in this. Since that time, a tremendous amount of momentum is being generated towards hydrogen at scale, and this whole process is a major opportunity to basically help increase hydrogen visibility in applications across sectors aligned with climate goals and other things. It's a critical time. There's a lack of proper education in the area, and when we try to evaluate and come up with optimized solutions for what our energy system needs are of the future, we need to make sure that hydrogen's properly vetted and included. A lot of what we've been doing with hydrogen at scale points to the importance of including it in that optimized solution, and that's hopefully something you'll be able to take away from this. Finally, hydrogen at scale, the big idea. This is the acknowledgement of the team. I'm getting to present this on behalf of our steering committee members who are listed in the top box. And then there's a number of different teams that we had put together on low temperature generation, high temperature generation, storage and distribution, utilization, the future electric grid, foundational science and analysis. And this was really the group of people who brought this idea together. What I'd say is in the last few months, we've really moved beyond this national lab team, and we're including many DOE offices and personnel, and then also other industrial and related stakeholders as well. So this moves me to why hydrogen at scale and what is hydrogen at scale. So a real key driver for this has been the greater acknowledgement of climate change issues, but hydrogen at scale does go deeper than that. But first we'll talk about the Paris Agreement at COP21. This is a quote from President Obama just talking about how we need to cooperate and we need to make a more prosperous and secure future, and that we require increased focus on renewable energy to make that happen. There's also been a lot of talk about mission innovation and accelerating the clean energy revolution. That's basically looking at doubling the amount of effort that's put towards clean energy by 2020. And so all of these things are pushing towards a greater recognition of the impacts of climate change, criteria pollutants, and other things. And that's really where hydrogen at scale can come in and play a major role. And I like to start off the hydrogen at scale presentations with the following two slides and talk about why hydrogen and talk about our energy system. The first time I saw this specific slide, I thought industrial age London or Pittsburgh, something in the 20s or maybe the 50s, based on how dirty the picture looked. I was actually shocked when I saw that found out that this wasn't 1920s London or Pittsburgh, but it was actually outer Beijing in 2016. So even though a lot of these things are no longer happening in our backyards, they're still happening and they're still impacting the planet, and we still need to do things about it. And it really points to this need to deeply decarbonize our energy system. And that's really where hydrogen at scale comes in. So hydrogen at scale does two things. It really enables green processes. And by green processes, I mean industrial processes and I mean transportation. They both can be made much cleaner. And it also allows for increased renewable penetration because it can help take the excess and potentially curtailed resources of that renewable and transfer it into these green processes. So if we basically allow hydrogen at scale to work, we can do things like use wind and solar and nuclear to basically run our energy system and satisfy all of society's demands. And while we're doing that, we can decrease all, what I'm going to show you is some preliminary analysis where we show how applying this can basically decrease carbon emissions by half by 2050. And that would be in line with the climate goals that we have, and it would significantly contribute to the administration's goal of 83% reduction of greenhouse gas emissions by 2050. So this moves me to what are the energy system challenges that we have. And what this really starts with is we have a multi-sector requirement. We need to take on transportation, industry, and the grid. If we take on just one of them, we can't meet these really aggressive climate goals. And when we also optimize each one of these systems independently, we don't necessarily come up with the optimum solution across all of our energy system. So even if we had a completely green grid, we'd still fall short because over half of our CO2 emissions come from the transportation and industrial sectors. Now, renewable energy offers a lot of promise in this area, but it's got a challenge in its variable and concurrent nature. And I like to show this graph over here, which was taken from Paul Denholm at NREL, where he talks about what happens as solar PV penetration increases from no penetration to 10%. And on this spring day that's being modeled, you can see even at 10% PV generation, the instantaneous generation of PV can go as high as 80%, and it can drive your system to overgeneration. And that's happening at a really low percentage, only 10% solar penetration. So to get to higher penetrations where we get to really aggressively take on the greenhouse gas reduction aspects of it, you can see how this concurrency problem can become a very big issue very quickly. And that's also highlighted in this more recent work also being led by Paul Denholm, where we talk about how much of your solar energy is curtailed as a function of solar penetration. And so what this graph shows is that basically as we increase solar penetration going from 10 to 20 up to 30%, the amount of curtailment takes off exponentially at different levels. These orange curves here represent today's grid. The solid lines represent the next marginal panel, the next panel you put on the grid, whereas the dashed lines represent the entire system. So at about 20% penetration of solar, you curtail about 10% of your electrons, but the next panel you put on the grid curtails almost half of its electrons. We can improve this slightly by going to a more flexible grid and maybe shift this out perhaps even as much as 10%, but we still hit these tipping points where we start to exponentially lose a lot of the value proposition of these renewable electrons because they can't be accommodated by the grid. And so one of the premises is that as we push towards higher and higher renewable penetrations, that curtailment will have an impact on the abundance of low-value electrons, and we'll look for solutions that service our multi-sector demands, not just taking on the grid, but also taking on industry and transportation. When I talk about this as well, when I talk about hydrogen scale as well, a lot of times what you want to do is you want to look to the places that are further ahead on this. And Germany is a good example based on how they've incentivized renewable energy. And what this graph shows is it basically shows their grid electrons as a function of year and as a function of the renewable aspects of them. So Germany has a goal of 20, 50, 80% renewable energy on the grid, but these are all projections. The data goes out to about 2014, where you can see that wind, solar, biomass, and hydro basically represent their renewable energy, and they're getting 28% of their grid through renewable electrons. They actually thought that they were projecting for a higher pathway, but even at this low level, they ran into curtailment issues and have tried to slow down where they stand. Now, the only difference in this graph between 2014 and 2050 is that they put much more wind and solar on to make this work. These variable renewable resources are the ones that are the most difficult because of these concurrency and variable generation aspects, and they'll need solutions to actually allow them to even keep to this forest green line moving up. And that's partially where hydrogen at scale comes in. So in this slide, I show the conceptual picture of hydrogen at scale as a role in our energy system. And so what we highlight here, and this is not a comprehensive illustration, it's just an illustrative example, are things like the variable inputs of solar and wind that usually produce electrons that run to the grid. You can look at other energy sources like concentrated solar and nuclear, which create thermal energy. And today we basically take that thermal energy, use it to make electricity. But you could also take that thermal energy and do things like produce hydrogen from it directly. Now from this grid, you can store those electrons either in different forms or in batteries, and they can be returned to the grid. But what also can happen is hydrogen, if you make it, can be stored and then also returned to electrons to the grid. When we talk about energy storage, it's often talked about in these terms of electrons to electrons, but that's actually disadvantageous at some level to hydrogen, because once you have hydrogen, much like these electrons, it's a commodity and it will run to the markets that demand it or will pay the most for it. And hydrogen has a lot more utility and a lot more flexibility than just being able to be returned back to electrons. Today, hydrogen's being put back into the natural gas infrastructure in places like Germany and power-to-gas applications, taking advantage of existing infrastructures to basically use its thermal energy downstream in other processes. It could also be put into these hydrogen infrastructure that either exists today or could exist in the future in larger areas. But again, if you're looking for the thermal energy, it's a potentially lower value proposition as well as the electrons. A lot of the value of hydrogen comes when you talk about these value-added applications, in particular the transportation, which is difficult to decarbonize. There's been a lot of work. The fuel cell vehicles that are on the road today have really taken on this green bubble for using hydrogen vehicles. But with hydrogen, you can also take CO2 and convert that CO2 into synthetic fuels or to methane. And today, one of the places where hydrogen is used a lot is in upgrading oil. But as we transition to more and more biomass in our energy system, biomass needs even more hydrogen than oil does on a per gallon basis because of how oxygenated it is. But then beyond just transportation, you can also talk about industry. So here we have the ability to take hydrogen mix it with nitrogen to make ammonia, which is going to be used for fertilizers. And the use of ammonia as fertilizers is increasing for two reasons. One is that we continue to grow more and more crops, and the other is that ammonia is displacing all of the other fertilizers that are being used. The other circle that we have down here is metals refining, and this is one of the more interesting ones. Somewhere between 7 and 10% of all greenhouse gas emissions today are due to metals refining. The picture I showed earlier of Beijing actually is from metals refining. It's not actually from power generation. Currently, the U.S. only has about 4% of the metals market, and a lot of it has to do with the environmental impacts of it. If we're able to basically use hydrogen as a reductant for metals, particularly iron and steel, we could potentially make a major impact in greenhouse gases and other pollutants in the area. And then once you have hydrogen, there could be other industrial uses, whether it's plastics or foods, where you could all of a sudden imagine new markets come up because we have this energy source around and it's kind of ubiquitous and abundant in similar ways to electrons for the grid. So that's the overall big picture of this. The next slides are going to transition into more detailed data analysis, and these slides will be available in case anybody misses them, because there's a lot of data in these slides, and they're actually somewhat of a challenge to present in this kind of a format. However, I'm going to move right to Sankey diagrams, and for those of you who aren't familiar with these are put out annually. Lawrence Livermore is the keeper of these, and they've helped us put these together. This is one that was put out in 2014 showing the nation's energy use, and that's about 100 quads. And so those are the things to think about. On the left-hand side of this graph, we have all of the different energy inputs for our energy system, whether they're solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, or petroleum. Those sources of energy funnel into the grid, and these are the electrons, and these are the useful electrons that are used in different applications, and then this is the rejected energy that goes off to the right-hand side. And then their end use is either in the residential buildings, commercial buildings, the industrial sector, or transportation. And you can see that only 40% of this 100 quads is actually for the energy services that we need as a society, and actually 60% of it goes into the rejected energy. But this basically shows how each one of these feed streams feeds each one of these services and end uses. Now the thing that's missing from this, and hadn't existed until our team put this in here, is hydrogen. Because hydrogen, much like electricity, could be drawn on this graph, and I do that in the following slide. So what you see here is basically now we've actually added hydrogen in, and oftentimes people will talk about, well, it may just not be big enough, but it actually, the 2.1 quads that runs into hydrogen is equal to that of wind and solar put together in 2014. Now this hydrogen's all coming from natural gas today. It's being made by steam methane reforming, and it's running into the industrial sector because both the upgrading of crude oil and ammonia production are considered to be industrial processes for the perspective of these Sankey diagrams. So this is how our energy system looks in 2014 in the role of hydrogen in the energy system. Now what our team has done has basically been to take this and take the annual energy outlook estimates for 2040 and see what happens if we do business as usual. And so if we do business as usual, I show that here, and you may not have noticed it. This is about 108 quads, where we were at 98 quads. But if I toggle between these two, you'll see qualitatively there's not a whole lot of change between them. Now, that means that basically if we do business as usual, the world in 2040 will look much like the world does today. But we know that we can't survive in a world that's like today, that our energy system's not sustainable. So if we instead look at a different future, where we say, okay, instead of keeping hydrogen at this level, we're going to increase the amount of hydrogen we're using. We're going to increase the way it impacts industrial and transportation applications. And by putting more hydrogen in, what we can do is we can increase how much wind and solar we put in while taking away some of these petroleum products. What we can come up with is a diagram that looks like this, where we've greatly increased the amount of wind and solar going into electricity generation. We're taking the extra electrons that would otherwise be curtailed, running them into hydrogen, and then using that hydrogen in different industrial and transportation processes. Now, our team has done some work to basically say what we could reasonably assume could be done by 2050. And so I'm happy to talk about that or provide more information for anybody else outside of this venue to basically talk about how hydrogen would feed into these industrial and transportation processes to make this happen. Now you could look at these two slides, the 2040 case versus the business as usual case versus the 2050 high renewable, high hydrogen, and compare them, but it's very difficult to do. So what we've done is we've basically combined these into what we call different Sankey diagrams, where what we've done is we show what we've taken away from the 2040 case by red and what we've added in the 2050 case by black. So this really highlights the power of hydrogen at scale when you look at how much natural gas, coal, and petroleum have been removed from this in terms of quads. In this case, I'll highlight that nuclear was reduced. It actually increases CO2 emissions by not keeping nuclear high because it could potentially offset some of these other ones as well. However, we took it because we had a base case that was chosen that was 80% renewable into the grid. And in order to make that work, we had to lower the nuclear number. And so you should think about this as an artifact and these other fossil decreases as targets. And these solar and wind increases as targets as well. You can see how much more solar and wind we put onto the grid, how much more hydrogen we have in the grid, and how that hydrogen runs into these industrial and transportation sectors. The other big number to recognize is this minus 24.7 number, which is because we've taken out these thermal inefficient combustion processes from the grid, we actually reject a lot less energy. So we actually need less energy because we're not using as much energy to cool towers and do other things in the power sector. I can reframe this, or we have reframed this, in terms of carbon dioxide emissions. In this case, the different Sankey is a little bit different. What we have here is that the gray plus the red is what would happen as business as usual. But the red shows that when we bring hydrogen in, we can basically take out 45% of all the CO2 emissions, or almost half, with 75% of the reduction coming from the grid. So if you look at what's coming into the grid by these red lines, we're actually removing 1,700 million metric tons of CO2 and only having 550 million metric tons remaining. So that's a 75% reduction of what's coming out of the grid. And then here in the industrial sector, we have 327 million metric tons that have been removed and 950 metric tons that are still remaining. And in the transportation sector, we've removed 400 million metric tons of CO2, but still have 1,200 million metric tons remaining. So what we've done is we've taken out 75% of the grid CO2, and we've taken out 25% of the industrial and transportation CO2, giving us about a 45% reduction in CO2 emissions from this. Now, what we haven't done is because we reduced nuclear so much, we lost other opportunities to take CO2 out of these systems. We also haven't let hydrogen run into the residential or commercial sectors where it could be used for heating value. And we haven't further electrified the transportation sector doing things like battery electric vehicles, which could take these numbers down as well. So this could be a big step in taking us to a greatly reduced CO2 emissions, but it would also benefit by having all of these other things be additive upon it. So the fact that hydrogen can do all these things isn't a huge surprise to most people. A lot of the arguments come down to, while hydrogen can do it, it's just too expensive to make happen. So what we've done is we've tried to look at what happens in the future and how this might change. And what we've done here is we've basically done some H2A cost analysis, and we compare basically the cost of hydrogen today, and this is not really today as this is scaled up to the gigawatt level as reflected by the capital cost, to steam methane reforming for hydrogen, which is how it's typically made today, and can be done at somewhere between $1.75 and $2 per kilogram of hydrogen. You can see for SMR, the main cost driver is the natural gas input cost, but it remains at about $2 per kilogram. If we talk about the cost of hydrogen production from electrolysis, if we scale up electrolyzers to the gigawatt level, current projections tend to come around $400 a kilowatt. These are made to run 24 hours a day, 7 days a week, so high capacity factors. But because they're at high capacity factors, they have to use the average wholesale cost of electricity input, which is relatively high at 6 cents 6.6 cents a kilowatt hour. Because of that, almost 80 to 85% of the cost of the outlet hydrogen is this electricity input cost. And that means that you want to run these things very efficiently, and you'll put more money into the capital costs of the system to basically keep this performance as high as possible. In the future, when we have more renewables on the grid and we have less match between generation and load, there'll be a time where if we're willing to do intermittent integration of these systems, we could potentially talk about just running them part-time, and this is an illustrative example showing a 40% capacity factor, where we're assuming that we can get electricity at a lower cost. And here we use 1 cent, just 1 cent per kilowatt hour, just as an illustrative example to show what would happen. We keep the same capital cost and the same efficiency, and what we show is that just by operating our system in a slightly different manner, we've completely changed the economics. Now the input electricity cost is a pretty minor portion of the hydrogen cost, and you can see that now 80% is either the capital cost or the fixed and operating cost of the system. And that tells you that if you need to make this cheaper through R&D advances, what you could potentially do is you could try to lower the costs of these systems while giving up efficiency. So this R&D advances is basically saying if we would lower the efficiency of our system to 60% in order to save some money and the capital cost of the system, we could drive these costs much lower. And this shows if you had 1 cent per kilowatt hour, $100 per kilowatt systems available 40% of the time, you would make hydrogen much cheaper through electrolysis than you could by SMR. Part of the reason that we think that this can happen is due to the fact that R&D investments on fuel cell costs have been so successful. Also, PEM fuel cell vehicles have been developed for similar operating conditions and ranges. So a fuel cell vehicle is made to operate for 15 years, turn on and off 6 times a day. And prior to having a lot of the research put into them, they, so in 2002, they had a very high capital cost of $275 per kilowatt. But over the past decade, through significant R&D investments, those costs have been brought down to something that's closer to $50 a kilowatt. If you recall the electrolyzer costs that I'm talking about on the previous page, I was only projecting to double that number. There are differences between PEM fuel cell vehicle systems and electrolyzers, mainly the operating potentials that they operate at. But to be able to operate them at twice the cost, because you're all of a sudden focused on the cost aspects of this rather than just the performance aspects of this, doesn't seem to be an unreasonable projection. And if we can do that, intermittently integrate them, then this really low-cost hydrogen becomes viable. However, there's a lot of things to do between here and there. So there's a number of things that we need to do to achieve hydrogen at scale. We've talked about these in terms of hydrogen generation, both low and high temperature generation. And what we need for these is low-cost, durable, and intermittent hydrogen generators. For the high temperature ones, we actually have to thermally integrate them as well. So the low temperature systems are inherently easier to turn on and off. The high temperature systems have to be thermally integrated more likely, but have a higher efficiency potential. So they're both of interest and both worthwhile to look at. But if we make the hydrogen and we can get the hydrogen made cheaply enough, we also have to consider storage and distribution. We've done a lot to basically consider it for vehicles and 700 bar refueling. However, when we talk about it in a larger position within the energy system, we have to be concerned about the safe, reliable, and economic storage and distribution of hydrogen. Things that I like to do as illustrative examples are talking about a wind farm that's in Wyoming, where the cost of building the infrastructure to take the electrons away is too expensive. However, you could store a week's worth of hydrogen on site and run a Haber-Bosch process continuously to deliver ammonia to an ammonia pipeline in an area where the economics wouldn't otherwise work out unless you had hydrogen as a specific energy carrier. And those are completely different storage and distribution cost concerns. In particular, in doing storage for vehicles, we have a really high premium on volume and weight. And in this situation, we'd focus primarily just on cost. And then finally, hydrogen utilization. Hydrogen is really a potentially game-changing energy carrier. It can revolutionize different energy sectors. It can do things in transportation and industry that basically allow us to be more green and more environmentally friendly. Now, when we put together these pillars of what hydrogen at scale needs, there's a number of cross-cutting issues that tie to all of these. We've looked at analysis because analysis is going to be a key piece of how you make each one of these things work. Each one of these has foundational or fundamental science challenges or things that can be drawn in to basically allow any of them to happen. And each one of these needs to tie to the future electric grid or the future energy system, because they'll all become coupled in some way as we start to fog the line between electrons and chemical bonds and hydrogen as a primary route to either direct hydrogen-hydrogen bonds or indirect route to carbon-hydrogen bonds, nitrogen-hydrogen bonds. We've set up a number of initial research priorities. I don't want to go through these in detail, just to say that there are things that we are looking at doing specifically for low temperature generation, high temperature generation, storage, distribution, and end use. Analysis will drive this. One of the things that's been happening is that hydrogen hasn't always been included or had tools developed to appropriately include hydrogen in analysis for full energy sector analysis. And really, full energy sector analysis is at a lower stage of technical development compared to some of the very specific tools that address just components of it. And this includes things like techno-economic and life cycle analysis as well, and then how we would connect to the future electrical grid and where there's gains in reliability and resiliency. So beyond that, we've also moved towards stakeholder engagement. So we've had a couple of workshops that have focused really on utilities and regulators, but we're also interested in how we basically engage with the industrial gas companies, big oil. We've been doing more now with the OEMs and the supply chain as well. We need to start making inroads with the metals community, the ammonia community, biomass upgrading. And then to drive all of this, the investment community is going to have to be a big part of this. So we've been focused on things like this webinar, different presentations, different workshops, and looking to put together working groups and websites as we start to roll this out and as we start to get more momentum behind it. So just to summarize the overall value summary for hydrogen at scale, it really comes down to reducing emissions across all sectors. And while greenhouse gases is what we talked about in this webinar a lot, we really need to focus on criteria pollutants as well. When I think about how this impacts the world and how China and India have real concerns for it, the criteria pollutants actually drive a lot of the local things, and this even is true to California and air quality in California, because hydrogen not only helps with the CO2 problems that the planet has, it also takes NOx out of auto transportation as a concern. And when it comes to metals and it comes to coal, things like arsenic, lead, particulate matter, and that's true both for the industrial and for the transportation sector for the particulate matter, all of those are basically zero emissions when it comes to hydrogen. Next, our work with hydrogen at scale has shown that it can support the needs of a dynamic variable power system. It's dispatchable, which is good for the grid, resiliency, and other aspects. It's scalable, and it's also one-way storage. It's not limited to just bringing electrons back to the grid. It actually takes that energy and moves them into these harder to decarbonize areas of industry and transportation. And it's really a unique potential of hydrogen to positively impact all of these areas, but it also does that by giving us these other benefits. So one is energy security. It's a diversity of energy. It can give you resiliency in that the grid is only transmission and it's not storage. Pipelines of hydrogen or geological storage of hydrogen provides both, so pipelines provides both transmission and storage. Geological storage or other types of tank storage can provide resiliency that goes beyond that. And it's also a domestic resource, particularly in the future where we're harvesting the local renewables to make it happen. These can allow us to be more competitive in a green manufacturing environment and lead to job creation as economies may turn to tariffs based on the energy that goes into the products that are being provided. And even just knowing that hydrogen is going to be such a large player having a role to play with the manufacturing of the devices as well is going to be a big one. And finally, in the pictures that I've shown of the entire energy system, because we're removing so much coal, so much natural gas that have large cooling towers associated with them, even though we're consuming water for the electrolysis that we're using, it actually comes up with decreased water requirements compared to the energy system. And beyond energy in the future, water is going to be a real critical concern. And so even though electrolysis to make hydrogen consumes water, the water requirements of our overall energy system would decrease substantially using this approach. And so that comes back to what does success look like? And I must have gone past this slide on accident earlier. But this slide represents basically the contract price from wind and solar. And it was put together by Arun Majumdar from data that came out of either the wind or solar offices of the Department of Energy. And it basically shows how contract prices in the last 5 to 8 years have come down significantly. This green line is wind and this purple line is solar. And this is one of the biggest changes that's happened in society. And me and my colleagues at the National Renewable Energy Lab would not have predicted anything this pronounced. And it really is one of the drivers for what we're talking about. Renewable energy is now getting very, very inexpensive on a per electron basis. And what that's meant is that our deployment, or this capacity in gigawatts, has gone up significantly. Now, this is a great trajectory, except for the problems that are coming in the future with the concurrency and variability that I talked about earlier. So as these trends keep going along, what's going to happen is that we're going to need to use more hydrogen to clean up these processes. And we're going to need more for ammonia. We're going to need some for transportation. We're going to need more to upgrade biomass. And so hydrogen is going to increase. But there needs to be a tipping point at some point. And it's going to happen maybe in the next decade, where we go from hydrogen from steam methane reforming to we go to carbon-free hydrogen. And then the transition will allow us to basically create an energy system that's largely CO2-free and removes a lot of these other criteria pollutants. So what we're looking to do is we're looking to go from this 10 million metric tons of hydrogen we have today to 50 million metric tons, so just a 5x increase in the amount of hydrogen that we're talking about in our energy system. But while we're doing it, we're going to transition from this hydrogen from natural gas to hydrogen from renewable resources or carbon-free resources. And we're going to go from 10 million of metric hydrogen to 50 million metric tons of hydrogen. And this will enable a 50% decrease in emissions by 2050 just due to this hydrogen at scale piece. And that will create a green world that has a bunch of these things. It comes with a decreased emissions by sector. It gives us more jobs, more security, more resiliency, and it helps us create a sustainable future, you know, for our children on the planet. And so with that, I'm ready to close and certainly happy to take any specific questions that you want to pass along to me.
All right, thank you so much, Brian. We will now start our Q&A. We've got a lot of questions rolling in here. And just a reminder, on the slide you'll see the questions box to where you can enter questions you would like us to ask Brian. So Brian, I'm going to start out with a couple of questions. There were two that came in while you were on the Sankey diagrams. And the first question is, does the charts or do these diagrams account for the efficiency losses in each sector? I don't know if you need a little additional clarification on that question or if you understand the intent.
So I think I do. So they do. And what you can see on this chart that's up now is that the efficiency in transportation is really low. So only 5.7 of the quads go to useful energy services out of this 27, whereas 21.4 of them go to rejected energy. As we get more and more efficient transportation, that percentage can change. And also over here, these orange are the useful parts of the grid, whereas the rejected energy is in this gray. So typically you can get the efficiencies by backing out the rejected energy portion from the energy services portion of these.
And then another question that came in that's related to that is, what is rejected energy? Can you clarify that?
Most typically it's heat. So there's the cooling towers in the electricity grid. So that heat is not useful. It's just rejected to the environment. In things like transportation, their useful energy is only the energy that it takes to move the system. Again, there's a lot of rejected heat energy. The braking that's not regenerative braking has a lot of rejected energy because that ends up as heat instead of the motive force that you're looking at. So in typical cases, the rejected energy tends to be heat, but it's basically energy that isn't exactly what you're trying to use it for, like creating a product. So industry is pretty good at it because the energy is used pretty efficiently, but transportation's pretty inefficient and the grid's pretty inefficient, and a large part of that is to do with heat cycles and the inefficiency of heat cycles in converting chemical energy into either electricity in this case or into mechanical motion in the case of transportation.
Thank you, Brian. So another question that came in, it didn't come in exactly as a question, but it was asking about whether hydrogen distribution would be needed if we have decentralized stations along the national highways.
So to me, decentralized stations is a distribution strategy. So the optimum solution, and it's one of the values in hydrogen, is that you can talk about doing this large centralized and then using pipelines or trucks, but you can also talk about running the electrical infrastructure and using the grid to do things locally at different places as well. And to me, the optimized part of that needs to be analyzed and modeled. And one of the powers of hydrogen is the flexibility that it has to either be done locally at a small scale or centrally at a large scale. And I would say that my feeling on this is that we don't know what the right solution is to all of the situations right now. That's certainly something that's important to look at and follow up on.
All right, Brian, and the next question, actually to build on that last comment and what you've already spoken about here, is asking what else can you add to how you see the market for hydrogen and renewable hydrogen evolving?
So we've had a number of, so we've had somewhere between 2 and 3 workshops that have included the utilities in this. And we started with the utilities because the utilities who run the grid are already running into problems. In nuclear plants are not being, they're being shut down. And in other places, the amount of renewables that are coming on the grid are getting so high that they're running into problems with, they recognize that curtailment will become an issue for them. And so when we look at this, the utilities have interest, recognize how their markets are changing going forward. And hydrogen is a large dispatchable load, has a potential to have a big impact on how they can address their mismatch between load and generation. Especially today, what's being done is that either natural gas fired peaking units are used as a backstop for renewables, and that's a great interim solution because it allows more renewables, and from a CO2 perspective, it's a lower CO2 emission. However, going forward, as you start making a lot of this hydrogen, the market will decide which go, and basically how big the infrastructure is and where it's available will have an impact on which one of these get hit first and how they get hit. Most of the hydrogen at scale picture is really a futurist kind of a 2050 vision. What we're actually coming to now is basically how do we make 2017, 2020 to basically see how this vision comes about. Because one of the aspects right now is that when different things are prioritized, what's driven a lot of what goes on is either the renewable portfolio standards drives how much wind and solar are going into the electricity grid, and zero emission vehicles are driving a lot of what's happening on the car side. We don't have anything specifically for the value of using renewable hydrogen to say make ammonia. The ammonia market doesn't have anything, whereas the fuel market does have some subsidies to drive renewable or low carbon fuels into that market. the portfolio standards also affect how much wind and solar are being brought into the grid. So what has to happen is we have to consider hydrogen properly, and we have to understand how policies are done and how that impacts where these go. I don't know that that's all of the right questions, but I feel like I don't know that I have the complete answer to that question. Those are just some of the components that will play a role in some of the pieces that have been coming together within the team for some of this.
Thanks, Brian. Got a lot of questions here. We'll see how many we can get through. The next one is the technology currently available to produce hydrogen from pure renewable sources?
Yes. However, you can buy electrolyzers today. There's a handful of companies that would sell you a megawatt electrolysis system today, but the production capacity of those, maybe globally, I would guess, is kind of like something in the 10 to 20, maybe even as high as 50 megawatts per year. It's far lower, and that would even be a stretch. Going to the gigawatt scale that we're talking about here is something where the manufacturing readiness levels aren't there. And when we talk about what you need to have cheap electrolyzers that integrate with intermittent electricity, that's at a technology readiness level that's at a lower stage as well. So there are electrolyzers that you can buy today. There's demonstration projects out there in Germany and in Southern California where this is happening today. We have projects at the National Renewable Energy Lab where we're taking renewables, we're making hydrogen, we're using them as part of a system like this. So the technology exists today, but it doesn't exist in an economical way to make this picture work. That needs advances in the technology readiness levels and the manufacturing readiness levels.
Thank you. Next question is, how can hydrogen upgrade biomass?
So biomass has a lot of the same hydrocarbon types of components. So when you talk about biomass, it tends to have lots of oxygenated species in it. Hydrogen is basically the way through reforming processes, so one type of upgrading or another, where hydrogen is basically put in to deoxygenate the biomass to give it higher octane numbers or higher energy density. So it's not necessarily specifically relevant for ethanol through fermentation, but other biomass routes will need more hydrogen to help deoxygenate them to raise the energy content of the biomass that goes in.
All right. We also have a question asking, says, you mentioned that hydrogen is 2% of U.S. energy. Is that energy production or energy consumption?
So that's the energy that goes into hydrogen from natural gas. So it's 2.1 quads out of this 98 quads. And 1/3 of that energy about is lost as rejected energy through the inefficiencies of the SMR process. And then 2/3 of that, let's say 70% of that, is useful energy as hydrogen that goes into these industrial processes. So it's 2% of the hydrogen energy.
Thank you. Have you examined any scenarios that look at decarbonization of fossil fuels to produce hydrogen?
So, I mean, right now, SMR, which is here, is just fossil fuel to make hydrogen. There's some other markets like carbon black, where you can take things like natural gas, make carbon black, and have a lot of leftover hydrogen. And so we have talked about it. I don't know how much we've looked at it, and a lot of it has to do with what's the capacity. You could certainly imagine a future, or at least I've thought at least some level, or we've discussed at some level about could there become a bigger market for carbon black? Carbon black right now made from natural gas is used in car tires, which is a big market, but could it ever be used in building materials as insulation materials or something else, so that you would basically do the same kinds of things and basically increase the amount of carbon black that was being produced. But certainly, you know, sequestering it or taking things like natural gas and taking the hydrogen out of it and leaving the carbon behind are routes to make hydrogen that could feed into this system as well.
Another question we received is, could hydrogen be utilized in an internal combustion engine initially instead of waiting for the fuel cell system cost to decrease?
So every car company has had a hydrogen IC, internal combustion engine ICE program at some point in time. None of them that I'm aware of currently have active ones. However, a number of hydrogen ICE vehicles have been on the road. And because hydrogen, so part of hydrogen's challenges is how it's a light gas and it's difficult to store. However, it also makes it really good within a piston for combustion processes. So it can be, but basically all of the car companies, all of the OEMs, they've gone away from that because the fuel cell technology is now demonstrated to itself to a level that it really would not make a lot of sense to go through the inefficient combustion process in the interim while the fuel cell technology status for the vehicles is pretty much there already. So I think that most OEMs would probably say they don't have any plans for hydrogen ICE vehicles. However, basically all of them have plans for fuel cell EVs.
Thank you. We also have a question asking how tri-generation systems would fit into this H2 at scale.
So tri-generation systems would have a number of different ways to fit in. One is kind of on the same lines that I had mentioned in terms of the carbon black routes, which is, you feed them natural gas, hydrogen comes out as one byproduct. So it would feed into all of these systems as well. But then the other part of these systems are, they can also be CO2 separators. What wasn't talked about in this presentation specifically was carbon capture and sequestration, and the tri-generation systems can play a role with that as well. When I present a lot of the numbers in terms of 50% decarbonization by hydrogen at scale, carbon capture and sequestration could add to that number as well. The tri-generation would add to it, and it's a potentially more effective use of the natural gas, and it's also I guess I lost that one. But it certainly fits in with the hydrogen part of it. The 2050 vision, and I didn't necessarily say this as clearly as I wanted to, is kind of a long-term vision. If you talk about what's going to happen in 2020 and 2025, you can see that hydrogen is still growing, but it's all still by SMR. Whatever we can do to basically use things like tri-generation to help chew into this earlier or to do different things are all great additions in terms of what happens in the interim versus the long term.
All right, we are running short on time here, so I'll give you one more question, and we'll have to follow up with the other questions separately. The question is, can you explain what could be done to accelerate the cost reduction of electrolysis so that it can become at parity to SMR?
Yes, and so the biggest part of this is that we need to. So we have these initial research priorities here, and this is the first things we would do. However, in the backup slides with this, there'll be a lot more discussion on it. But we need to develop and test durable systems for variable operation. The intermittency, the coupling with intermittency, is the knob that you have to get at, because if you can't get at low-cost electrons, you're not going to be cost competitive. And the truth is that we don't have a lot of low-cost electrons around today because we just don't have the renewable penetrations that will drive them, but they'll be here in a decade. And then these technologies also have to be there in parallel so that they can basically symbiotically enable each other to move forward. And so we talk about developing different ones. I think that there's probably, no, this presentation doesn't have it, but there's, in the backup slides, I talk about more things that can be done. So there's big things like power electronics, integration, this intermittent applications as being real focal points for how you would bring these costs down to make them more in line with kind of the PEM fuel cell vehicle systems.
Thank you, Brian. We have a lot of questions that we simply do not have time for today. We will respond to as many of them as we are able following the webinar. Brian, thank you again for giving this presentation and leading this effort. I'm going to now turn it over to Chris to wrap up.
Yeah, thank you, Brian. Great presentation and really great Q&A at the end there. Certainly appreciate you coming out and putting on this webinar for us. Erica, thank you as well for moderating today. That's going to conclude our program. If we didn't get to your questions, as Erica mentioned, please feel free to email the FCTO webinar mailbox. Brian, if you want to go to the thank you slide at the end there, we can show all the attendees the email address. Okay, there we go. DOE Fuel Cell Webinars there. For any follow-up questions, we will capture all the questions that you submitted today through GoToWebinar. Thank you again for everyone for joining in. I'll remind you that the webinar and slides will be available online at the Fuel Cell Webinars website. That's shown there at the first link at the bottom. Those will be available in about 10 days. Also, I encourage everyone to sign up for our monthly newsletter, which includes information and registration for upcoming webinars. You can sign up for that at the second website shown there at the bottom. And that's it. Have a great rest of your week, everyone. Bye-bye.